All right. Hey, everyone. Welcome to lecture number 7, I believe. Welcome. So we've had our first big, set of due dates that you've just kind of gone through. So hopefully you're all still alive and have survived. So Arvin is going to share some results from the programming challenge, which I'm excited to see. Looks like overall you guys did pretty well. So great job. You've made it through your first programming challenge. Way to go. Cool. So yeah, I'll go ahead and hand it off. So Arvin, if you don't mind doing a screen share, and maybe you can walk through the results from the programming challenge.
Sure, Professor. Yeah. You're able to see my screen, right?
Mm-hmm.
Okay. So we had total 56 submissions as of now, and out of which around 32 had a 10-pointer and few 9-pointers. Let me show you this quick. Yeah. So yeah, this is the analysis. We had 32 students with 10 pointers and 12 students with 9, and one with 8, 2 with 7. It's good that half of the classes have scored 10.
Yeah, that's great.
And this is a distribution of the accuracies as well as the pointers. We had this is the distribution, like from 0.6 to 0.73. 0.73 is the highest. Actually, Nick was leading this scoreboard until yesterday night.
Oh,
But
wow.
all of a sudden, one student, she submitted it 45 minutes before the deadline, and she got 0.73.
Oh, wow, man, that's heartbreaking, right? To be in the
Yeah.
lead and get it, but that's awesome. Congratulations.
Yeah, and this is the accuracy thing, and 10 students, around 10 students are above 0.7. It's really good.
Very good.
And yeah, these are the distributions for easy, medium 1, medium 2, and hard. Looks like majority of the people did good with the easy ones, but the hard ones, medium and medium 2, you could see only 0.33 for most for these 3 categories. This is expected, especially for the hard ones.
Yep.
And this is the histogram for execution times. Most of the 46 students could actually run it below 70 seconds. Yeah, this is good. I think,
Great.
and this is the I think these are the ones who got zeros, I guess, on the leaderboard.
Right.
That's it.
Great. Excellent. Well, yeah, thank you, Arvin. That was awesome. Yeah, so we don't have a time versus accuracy chart, Abhijit. I think that's the one Arvin didn't make this time. We've shared that in the past. Maybe we can make it later if we have time. But it is cool to see time versus accuracy. That gives you kind of another dimension. Well, great. Yeah, thank you, Arvin. That was super helpful. And yeah, overall, I'd say I'm very pleased. I think that you guys did well. You always make me nervous by waiting to the last minute. But yeah, and if you want to, just throw up any comments. Let's just open it up for conversation while we're on the topic real quick, and then I want to make sure that we cover all the other announcements with Arvin and Rohan. And then, so Sahil says, could you consider the best score so we can keep experimenting? Can you expand a little bit, Sahil? Consider the best score. So I think we'll keep the evaluation server open a little bit longer, but we have closed the gate for the award. So if you're going after the $10 gift card, that's done. That's the official due time. But you're welcome to keep experimenting. That's fine. I'm not sure how long we'll keep AutoLab open. Do you guys know when we'll shut down that challenge? I don't think we need to close it right away or anything.
Yeah, it'll be till October 1st, like the 3-day thing.
Okay, perfect. Yeah, so you have 3 more days if you want to keep experimenting. Great. Excellent. And yeah, just while we're on the topic, and we'll come back to some more announcements in a second, but just while we're on the topic, what did you guys think of the first programming challenge? So feel free to throw it in the chat. Was it harder than you thought, easier than you thought? Did you learn anything? Was it a waste of time? What did you guys think of this challenge? Got fun? Enjoyed it? Great. A lot tougher than I thought. Yep, sure. A lot of trial and error. For the folks who thought it was harder than they first thought, and that's kind of the point, it's supposed to be kind of hard, right? What made it hard, right? What made this challenging? So for example, if I get a 9 on my 4th attempt, I won't be, okay, yeah, sure. Processing time made it hard. Yep. I struggled with the hardest identifying patterns. Yep. The execution time. Absolutely. Achieving this. That's a good one from Videhi. You're saying that what was hard was achieving the sweet spot of thresholds. Yeah. So Videhi, you have really captured one of the big challenges in traditional computer vision. It's tuning all these thresholds, right? And deep learning is going to do away with that. That's a big challenge in computer vision. Very well said. Sticking to NumPy was hard. Thomas says getting the computer to understand what lines meant. Yep, absolutely. Finding thresholds, absolutely. Yep. Time complexity, yep, absolutely. Not using imports, yep, totally. Yep. So yeah, these are very common challenges. Hopefully you guys, everything was hard. That's funny. I thought it was tough, but it was super fun. It was nice to chill out in the evening over coffee and at night and work on it. That's great. Awesome. Cool. I liked the brainstorming sessions we had as a team. That's awesome. So hopefully I'm saying your name right. I think it's Aparajitha, I believe. That's great. Very cool. I'm glad that you enjoyed it. That's super cool. AJ is fine. That's easier. Well, great. Good. So yeah, we hope this is a good challenge for you. I'm sure some of you didn't like it, and that's okay. But it is a little bit different than some challenges. But it sounds like some folks did enjoy it, so that's great. And I promise this is a good way to start computer vision. This will set you up well for the course. So great, good job, guys. Cool. I want to hear if you guys have any feedback on Tony Fast before we go on. But before that, actually, let's go ahead and go into that, and then we'll do the rest of the announcements. So just while we're kind of chatting real quick, yeah, what did you guys think of our first guest lecture? Good use of time. Is there anything specific you liked from it? What are your thoughts? So we got Tony was awesome. Great, good. Yeah, he's a really nice guy. He's super smart. He is high energy. Yep. All of our guest lectures will not be so high energy. It was awesome, right? Yeah, they don't expect that from everyone. It felt great, but too open-ended. Yep, that's a fair point. Yep, absolutely. So I think that's something that you'll see in the future guest lectures will be a little bit more focused, right? So yeah, it's a trade-off thing. I think from Tony's guest lecture, what I really wanted you to take away, part of what I wanted you to take away was just, there's a lot of different ways to approach these topics. And it wasn't like a deep technical lecture where we're going to dive into one really specific thing. So yeah, and in the future guest lectures, you'll get more of that. But I'm really glad we had Tony. I think that he, adds a lot of perspective. Any other comments about the guest lecture? Yeah, and it was a bit of a conversation, right? Learned a lot about using Python in different ways. Great, cool, that's great. Cool. All right, so let's hop in. We'll have another guest lecture, and I think next week actually, and it'll be from this guy's going to be cool. It's going to be from Mark Hayworth. He is a computer vision expert at Procter & Gamble. He has a huge experience in creating computer vision algorithms for all kinds of computer vision problems. That's going to be really interesting, I think. Great. Okay, cool. So let's go over announcements. I'll just walk through the schedule a little bit here. Before I do, though, Rohan and Arvind, what announcements do we have? I'll just walk through the schedule in a minute here. Any announcements? One announcement for sure is that we're working on project groups. I think we'll have those assignments out by the end of the week. We're going to meet right after this to discuss project groups. Any other announcements, Arvind and Rohan?
Nothing, I guess. I think some of the students did not submit it on Canvas, the assignments.
Oh yeah, be sure to submit your programming challenge on Canvas because that's how we're going to record your official grade.
Yeah, I think quizzes. Everyone has taken the quiz.
Great.
Yeah, I think.
Okay.
And regarding the Thursday lecture, maybe once
we
can make an announcement about that.
Yeah, thank you so much. Yeah, so just so you guys know, Thursday's lecture may be pre-recorded. I've had something come up last minute and I may not be able to make it. What we'll probably do is I'll pre-record the lecture for Thursday and you can watch that at your convenience. And we may have a Q&A session with Arvind and Rohan on Thursday during class time. That's what we're planning on roughly right now. We'll let you know in an announcement later today or tomorrow, though, what we're definitely going to do. But you may have a little extra flexibility on Thursday.
Quiz results, maybe by the weekend.
Yeah, probably by the end of the week or so. We've got a little grading to do. Can we not have quiz and challenge due same day? Maybe. Yeah, Ghana, that's a fair question. We have them kind of lined up right now. We'll take that into consideration. We do like to end, the challenge for us, Ghana, is that we do the class in modules, right? And we want to kind of finish a module and start the next one. So I would encourage you in general to start earlier on your programming challenge so you don't feel as rushed. We'll take your question into consideration though. But there's a reason we do it, basically, so we can finish up the module. Well, the solution to the quiz we discuss now, that's something we've done in the past. We are not going to discuss it right now, but we could do it on the Thursday lecture, but it's going to be recorded actually. That's actually tricky. It's a great question. Let's discuss that after class, Arvind and Rohan. We may have to do a non-recorded part of the lecture to discuss the quiz solutions because we don't want to post that on YouTube because the future quizzes will be similar and we don't want to give away the answers.
Yes.
That's a good question. We'll get back to you on that. Good question. Great. Any other questions from the class or announcements from Arvind and Rohan?
One thing is I want to ask the students to start the programming challenge a bit earlier.
Yes.
Because the past 2 days we had many questions pouring in. It was a bit difficult to answer every question.
Yeah, so by starting the challenge earlier, guys, you're being kind to your TAs. So Arvind and Rohan work really hard to make this class great for you guys, especially this semester. My schedule's been a little bit more complex than it has been in previous years. So Arvind and Rohan really do carry a lot of the weight. So by starting earlier, you are doing them a favor. Great, and then Vaishnavi, you have a question about timing. I would say send us an email about that, and we'll get back to you. You're asking about, yeah, thank you. Cool. Okay, great.
Actually, maybe
Yes.
around 10 people have submitted it on Canvas today. So it is considered actually according to Canvas, but we'll let you know once we decide.
Oh, you're asking about the Canvas submission. Yeah, actually, that's a great question. Yeah, so a lot of folks have submitted today. We can probably offer a free grace period day for that. We'll discuss after lecture though and let you know for sure. All right. Okay. All right, great. All right, cool. Can you answer the best score question? Oh, I see what you're saying. So Subham is asking about, we've done this in the past, I think, guys, where in AutoLab there's no way in AutoLab though to take the best score instead of the last score. But we've done that do you remember if we did that last year, Arvind and Rohan? Did we do that for your class where we took the best score on AutoLab instead of the last score?
We took the recent score and not the best score.
Say again?
We took the recent score and not the best score. So we used to take the recent score and not the best score among what they submit.
Okay, yeah, so that's what we did last year, guys, and that's just how AutoLab works. Again, we can discuss that and get a final answer to you, but I think that's just a limitation of AutoLab, unfortunately. If we could make it take best score, we would do that, but actually, I don't know if we're able to look at the history. We might not actually have the technical ability to take your best score, but we'll discuss and we'll let you know. It's a good question.
One thing the students can do is they have the hand-ins history available. They can download their previous submissions with which they got the highest accuracy and they can submit it just to maintain the highest score.
Oh, I see. They could resubmit basically with the same submission that achieved that highest accuracy.
Yeah.
Okay, gotcha. Yep, that makes sense. Does that make sense, guys? So for example, if I get a 9 on my 4th attempt, I won't, yeah, I understand. We understand. This is a question we've gotten in the past. Yep. Great. And yeah, we will, so Chandan says we'd be wasting 1 attempt. Sure. Yeah, I understand where you guys are coming from. We need to get into lecture for now just to make sure we have time to get into this new area. But we understand your concern and we would like to help you and we'll do our best to. We'll discuss after lecture and we'll come back with our policy. If we could just take the highest automatically, we would do that, but unfortunately AutoLab doesn't make that easy. So we will let you know what our policy and decision is later this week. We'll discuss and we'll let you know, but we understand your concerns. Cool. Okay, great. All right, anything else, Arvind and Rohan?
Nothing from my side, Professor.
Great. All right, thanks guys, cool. All right, so let's hop into learning to see. Yep, let's get started, cool. So yeah, we appreciate your questions. I love the dialogue. Great, all right, cool. So new module, and I do wanna get started because we have squished this module into 2 weeks and actually only 3 lectures. So it's gonna be quick, but it's a good module and it's not a terribly difficult challenge, I would say. I don't think it's gonna be as hard as the original problem. There is a lot of meat here though, and we're gonna really get you into machine learning. So machine learning is kind of the force that's sweeping the computer science world right now. It's changing a lot of things in computer science. So having an understanding of machine learning is really, really valuable, and this is gonna be your introduction to machine learning for computer vision. Let's see here. So the next thing I'll say is that this series, or this module, follows a YouTube series called Learning to See. So a lot of the stuff you're going to learn, you can actually learn from just watching the videos. In lecture, we're going to be doing a little bit more Q&A, a little more hands-on stuff. But you have the ability in this condensed 2-week period to go to watch those videos at whatever pace makes sense for you, and you can get a little bit ahead if you want to. We're not going to be quizzing you and testing you and expecting you to understand everything in that series. It's a pretty long YouTube series. It's about 15 parts. It's probably an hour and a half of content, something like that. But it's not terrible, but it is pretty dense, basically, right? So it'll cover a lot of stuff. But the real thing that I hope from you guys in this challenge, in this module, is I really want you to start to get your head around the concept of machine learning, some of the challenges, some of the pitfalls. You know, what is this machine learning thing? How does it work? And what should we be paying attention to? So tonight or before Thursday, you'll start watching this. Actually, no, the way I had this set up is I wanted you to watch part 1 before today's lecture. So hopefully you've had a chance to see it. If you haven't, go watch it afterwards, but this is the first, this is an ad for SAP. But after that, you can check out the first part of this video series. And then for before Thursday, you'll watch parts 2 through 5. So this will really kind of ground the series, and it'll give you a lot of stuff to pay attention to. Okay, so let's hop into it. There is a challenge in this programming, in this module. And let me just lay out the challenge for you because it has a lot to do with the module. The challenge is this. So this little device that you see on my desk here, let me make this a little bit bigger. This is what's called a Leap Motion infrared camera. It has 2 little cameras in here. It takes infrared pictures. That's why this looks so dark, because it's not using visible light, it's using infrared light. And the challenge that I've laid out for you to solve is to count the number of fingers that are being held up, right? So maybe this is easier than brick, ball, cylinder. Maybe it's harder. We'll see. I think in practice, you'll find it a little easier. We're going to walk you through this whole kind of process of building a machine learning model that can be used as part of an overall solution to this problem. The machine learning model we're going to be developing is called a decision tree. Decision trees are the most popular machine learning model on the planet. They're a very successful model. They aren't used in computer vision as much as they used to be. Today, neural networks are much more popular. And you'll see that our next module is going to cover neural networks, so get ready for that. But a lot of the principles that you're going to learn in Module 2 by setting up decision trees are going to apply for the rest of the course. So we're going to really focus on the general principles of machine learning, and we're going to do that by training decision trees. But you really won't use decision trees for the rest of the course. But decision trees are something that I want you to be aware of, and they're very useful to have as a general machine learning practitioner because they're still very popular outside of computer vision. So they're worth investing in, and they're one of the simplest machine learning models to learn, so it's a great starting point. Machine learning decision trees are a really good point to start for machine learning. Okay, and what I'm showing you here is a successful algorithm that counts fingers, and this is what you're going to be basically developing in this class. Again, this is going to be pretty open-ended. There's not going to be one way to solve the challenge. There's a bunch of different ways to do it. So as you're looking at the challenge, I encourage you to look at different options and be creative. I'm not going to hand you the whole solution. As you look through this notebook, this is the notebook that describes the challenge. I encourage you to look at the guidance that I'm going to provide you. I'm going to give you a little bit of some tips about what we're going to do in the course, how we're going to make these rules to find fingers, stuff like that. I'm going to give you an idea of kind of some approaches you could take. So I'm going to give you a little more guidance than last time. But again, it still will be fairly open-ended. So that's going to be the challenge. And with that in mind, let's go ahead and get into our first lecture. And this will be really, it's pretty interesting. I hope you enjoy this little series. We're really going to be getting into how do we learn from data? Like that's really the big question we're going to work on addressing. So as we get into this, let's go ahead and start by looking at our data set. So I have provided you with a data set of my hand. So here it is, I took this data set. And in this data set, I'm holding up 1, 2, or 3 fingers. And this data set includes labels. It includes both the images, as you see here, and it includes the ground truth label, which is the number of fingers that are being held up. So that's the data set. There's 42 examples, as I mentioned. And what I want us to do is let's start thinking about, how can we solve this problem, right? So you've just done brick, ball, cylinder. This might seem a little harder because I'm sure a lot of you used like, the Huff transform, things like that to find lines. And there's going to be some lines in these images, but they're not going to be as clean cut as the brick, right? There's going to be some new challenges. And we're actually not going to use the Huff transform or edge detection. You can certainly try those techniques, but the technique I'm going to be walking you through, we're going to use a technique called machine learning. So instead of writing rules to find fingers, ultimately we're going to be learning rules, which is pretty cool. So let's get into that. Okay, so here's the data set. All I've done here is I've just done a little threshold. So I've just said, okay, let's just threshold our images so we have these nice binary images of fingers and we can still see the fingers so we can count them. So I've made our problem a little bit easier just by taking a threshold. So that's the first thing I've done here. Let's see if things run live okay right now. Let's see how my MacBook is doing. Yeah, there we go. Cool. All right. Okay, so what I'd like us to do is focus on a little sub-problem. So the sub-problem is this. So instead of trying to count the fingers right away, let's try to figure out which pixels in our images correspond to fingers. So what I mean by that is that, hey, here's this finger, right? And hey, this pixel, that's part of a finger. This pixel is part of a finger. This pixel is part of a finger. This pixel is not, right? So let's start with that simple subtask, right? Can I break apart the problem instead of just trying to count fingers all at once, right? Can I first try to figure out which pixels show fingers? So that's the first thing we're going to try to do. Which pixels correspond to fingers? Okay, and to do this, I'm just going to grab a little bit of data here. Let's see. So I'm going to grab, let's see, just 3 images. Here they are, 1, 2, and 3. Cool. Okay, and maybe I'll talk through a little bit of the Python here in a second. Let's see. Okay, yeah, sure. Okay, cool. So I'll talk to you some of the Python that we're doing here. It's not too exciting, and it's not, let me go ahead and hop to here. Yeah, here's what I want to hop to. Cool, okay. Great. So I've written a background method, and let me zoom in a little bit here so it's really easy to see. Okay, cool. And I have video and audio working right now. Let's not jinx it. I shouldn't have even said that. But if the audio gets bad, I will turn off my video. Okay. So here, I have this little method I've written for you guys called extract examples from list. And what that does is I'm giving it a list of 3 indices, right? I'm saying, hey, take these 3 images, right? And I'm extracting a bunch of little windows. So let me back up just a little bit here. So remember, the key idea here, right, is can we make a decision for each individual pixel by looking at its little neighborhood, right? Can I look at the little 9x9 grid or a little neighborhood around our pixel? There's nothing magical about 9x9. I just chose it because it worked well. But that's the subtask I want us to think about. Can we write an algorithm that figures out if a pixel is part of a finger by just looking at the 9x9 neighborhood of the pixel? Now, to do that, we first need to extract those 9x9 neighborhoods. So that's what we're doing here. So down here, I have this little helper method, like I said, that I wrote that pulls out the examples. And what I want to just show you briefly is kind of the shape of our data for this challenge. So I'm getting out this thing called X, and I'm getting out this thing called Y. And what I'd like to discuss just briefly here is what do those represent? Because this is going to be a very common representation in machine learning. And I just made my screen a little bit bigger. Okay, cool. So yeah, so I'm printing out the shape of this thing called X and the shape of this thing called Y. All right, so throw it in the chat window. Why are these the shapes of this thing called X and this thing called Y? What are we looking at here? Yeah, data and labels. Yep, right. So Videhi, Pooja, good. So Y is like our labels, and we'll get into that in 1 second. Let me go ahead and comment this out. Cool. And X, so what is X then? So if Y is the labels, then what is X? Yeah, X is like our input, it's our data, right? Okay, cool. Can someone, audio issues, all right. Spy to the video, all right, video was fun. Okay, how is audio now?
It's good.
How do I sound? Better, good, okay, great. So video was fun while it lasted, okay. So now this 7867 by 81, right? Any guesses? Why is that the shape of the data that I've extracted using this method that I read? I haven't shown you the method. I'm just saying, hey, here's some method that is going to extract the data we want to work on. Why 7867 by 81? What's going on here? Matrix, okay. All right, related to 9, sure. We'll get into this in 1 second. Yep, absolutely. Let's come back to this in a second. Before we do that, can someone tell me the 7867? Like, why is that the first dimension? Any guesses on that number? And remember what we're doing here is I've taken these 3 images, and I want what I've told you is here's a method that's going to extract these individual examples, right? And these individual examples are going to be just 9 by 9 grids. So what that number actually means is that I'm taking these 3 images and I'm extracting every possible 9 by 9 grid. Okay, so I'm iterating through the columns. I'm taking every 9 by 9 grid I can, right? And I'm putting those in this big matrix. So there's 7,867 examples. That's how many 9 by 9 grids exist in our 3 images. And we'll get into that more in a second. Let's talk about Y for a second. And did I gloss over something? There's one important kind of point. Did I gloss it? No, I guess I didn't gloss over it. No, I didn't. Okay. All right. Cool. I thought I did. All right. Okay. What I want to get at, though, we'll come back to X and Y in a second. What I want to get at is let's look at one of our examples. So the code up till this point is not terribly important, but now I'd say it is important. So let's look at my little code snippet here. So what I'm doing here is I'm saying I'm finding an example to show, and I'm taking X. And what does X of 600 comma colon do? And let me, that's the worst. Okay, 1 second. Okay, I think I'm back. Yep, I'm back. Cool. Okay. So remember, X is of this shape, 7867 by 81. So what am I doing with this? So just this first part. What would you say in words that I'm doing here? Any ideas? Good guess. Good guess. Matrix number, kind of getting there. So what I'm doing is I'm actually taking the 600th example. Yeah, or the 600th matrix, right? Yeah, I'm taking the 600th example in our data set, and I'm reshaping it to 9 by 9. So basically, this is very common in machine learning. We're going to take our images and we're going to ravel them or unroll them into vectors of length 81. And to make them back into a little grid, I have to reshape them back to 9 by 9. So this is one little patch. This is one little patch of one of these images is what we're looking at. Remember that we did a binary operation. So the reason it's black and white is because we did a binary threshold as well. And if I did 601, for example, I'm going to see here's the next window, for example. And I could do 602, here's the next example, and so on and so forth. So that's the idea with that method is we're getting out our data. And let me come back to the problem at hand, though. And what I really want to talk about is how could we write a rule? How could we develop an algorithm to find fingers? That's what I really want to get us thinking about. And this image, this might show a finger. Maybe it could be one of those patches that shows a finger. It kind of looks like it, right? If I go back to here, this patch had a finger. It looks kind of like a finger, right? So this might be showing a finger, maybe. And let's think about how we could write a rule that would help us find fingers in these images. And just to remind you, that this 9 by 9 grid, it's really just a set of numbers. It's a set of zeros and ones. And I can also just show it as a matrix, right? So, this is the same thing. It's just a matrix of zeros and ones. And now what I want to get us into, and we'll do this in the video as well, I want to get us into thinking about how can we write a rule that will describe what fingers look like. That's what I want to get us thinking about. So let's see here. So Sahil says the image path shouldn't have all zeros or ones. Okay, let's get into this in a little more detail. Yeah, so I like what Supreet is saying, sets of ones sandwiched between zeros. And Thomas says white on both sides. Yeah, exactly, right? So that could be a rule we could write to help us find fingers, right? And I think if you look at what I've done here, I've said, okay, let's make a rule that's really just gonna be like pattern matching. Let's say that if we find a pattern like this, and let's look at the pattern I've set up here, right? I've just done zeros on the sides, right? And then ones in the center, and then zeros on the sides. So really, if we visualize this, which I do right here, it's exactly what Thomas said, right? It goes white, black, white, right? So this is a simple rule, but what we can try to code up here is we can say, okay, for the parts of my image that match this pattern, those must be fingers, right? So it's like a simple rule we can use to find fingers. So that's the idea here. And I'm starting us with a simple strategy. We haven't quite touched machine learning yet, but we're getting there, I promise. To really understand machine learning, it's helpful to first think about a simpler solution like this, where we just develop rules ourselves, and that will help us understand how machine learning is going to work for us. Okay, so here's a simple rule that we developed. We said, hey, if a pattern matches this, if a 9 by 9 grid matches this, then it must be a finger. So that's a very simple rule. So what I'd like to do is let's go see how it does. To figure out how it does, it's actually pretty straightforward. I'm going to use a little bit of fancier Python. It's not too bad, I promise. Basically, we take x, which is our big, remember x is our big data vector, and you'll start to see why we have x shaped this way. Just real quick, so we cover a little bit of Python here. What does Ravel do? So throw it in the chat window. What does Ravel do? R-A-V-E-L. Yeah, it flattens an array, right? Cool. So let me just show you this real quick. When I press Shift Enter to run this cell, what will the result be? So if you know the answer, throw it in the chat window. What will be the shape of rule.1.ravel? Okay, remember this is rule.1, so good guess, Monica, but this is not all of our data, it's just rule 1, right? And let me do one more thing for you real quick. So remember rule 1, that's just this simple 9 by 9 grid of a rule that we made. Yeah, so I think it's just gonna be 81, Austin. Yeah, so let's have a look. Yeah, so it's just 81 is the shape. Cool. So what I'm doing here is I'm computing the difference between our big matrix and our single rule. So I'm actually taking a matrix minus a vector. What this does is that for every row of that matrix, it takes the difference between that row and the rule, basically. And if the rule perfectly matches that row of our matrix, then the difference will be 0. And I'm actually finding all those rows by using this operation called np.where. So a little bit of fancier Python here. I wouldn't worry about this too much. If you're interested in improving your Python skills, you could look at this line as an example and kind of break it apart to see what I'm doing. But it's not too bad, I promise. Just know that the output of this is the rows where we have an exact match. So yeah, Austin said, what does the tilde do? So I believe the tilde in this case is a not operator. So in Python, you can use exclamation point for not in some context, and in some context you use tilde. I'm trying to remember when you use a tilde. I think it's when you have a NumPy array. I don't want to get too off track here, but let me just do a quick example. So if we do 0, 1, if I have a NumPy array like this and dtype equals bool like that. So I'm making a Boolean NumPy array. There we go, cool. There's a very simple NumPy array. I think if I put a tilde in front of it, yeah, there you go, cool. So a tilde inverts a Boolean NumPy array. That's what it does. Sometimes in Python you'll see like exclamation point equals. That means does not equal, but that only works for logical operators, not for NumPy arrays. So I don't think I can do this. Yeah, I can. It actually does something way different, right? So if you want to take the inverse of a NumPy array, you do tilde. So good question. All right, cool. Okay, so let's get into showing these matches. So we made this rule, and our rule said, hey, whenever I see this pattern, it must be a finger, right? And I looked for matches, and I found these, which it doesn't seem like a lot of matches. We'll get into that in a second. And now I'm going to visualize them. So I have a little method called visMatches, and it does what it sounds like. It shows the matches to our rule. So hopefully the screen share is coming through okay, and you can see the 3 little green pixels here. And hopefully you can see, or sorry, there's 4 here. There's 3 little green pixels here, and there's 2 little green pixels here. So let's pause and reflect for a second. How did our first attempt at writing rules to find fingers do? How did we do here? What do you guys think? Good, bad, medium? How are you feeling about our first rule to find fingers? Okay, so found the first finger, only 1 finger, okay-ish, but not satisfactory. I agree, right? And remember, we're trying to find all of the pixels that correspond to fingers, right? And there's a bunch of pixels we've missed, right? Okay, so in words, what's the problem? How would you improve this, right? So our little rule, which our rule said, hey, find patterns that match this, right? Yeah, how could we make this better? Any ideas? Make the matrix wider, okay. Not a big enough patch, okay. Fingers too thick. It's identifying only fingers that are straight. Yeah, so yeah, that's a really good point. Hopefully I get your name right. Mahesh Sharwa, I think, or Sarwa. Apologies for the name pronunciation, but yes, that's a really good answer. You said it's identifying only fingers that are straight. Yeah, good, good, good. Yeah, so we need maybe more flexible patterns. So let me propose something to you. Get ready. Okay, so here's my proposal. Let's make some better rules. And what I did to make a better rule is I did this. Let me show you what I did. So I made this big fat array. It's bigger, right? And I kind of made this nice finger shape. So it has like a nice kind of top to it. And what I do is I run through this big rule to sample, and I make a bunch of sub rules. Let me show you. So what I do is I take that big matrix and I sample it in a bunch of different places. I grab little patches of it, and I end up with all these rules. So I end up with 30 new rules. And the rules are whenever we see a pattern that's like any of these patterns, it must be a finger. So that's what we're going to try next, right? So now we have 30 rules, right? So we should do better, right? I hope. Hopefully we do a lot better, right? That's our hope. So let's get into it. Hopefully that makes sense. I've just taken this big pattern, and basically with this for loop right here, I'm just taking little 9x9 grids of this overall patch to make these individual 30 rules. Okay, so let's have a look. So we have 30 rules. Length of rules is 30. Let's try them out. Let me go ahead and run this code and maybe make your prediction now. What do you think it's going to look like? So here are the results. Here's the results of using 30 rules to try to find matches in my image, to try to find fingers. Okay, throw it in the chat window. Are you happy? How have we done? What do you think? Good, bad, medium? Austin is not happy. Sai is not happy, okay. All right, the other Sai is neither Sai is happy. Okay, good. That's funny. All right, cool. Unreliable, needs improvements. Okay, cool. So it's not doing great. So first of all, it's not capturing all our finger pixels, right? It's missing all these pixels, missing all those pixels, right? Okay, cool. What else is it doing wrong that's maybe a little bit concerning? What's it getting wrong? It's not getting the tips, totally, I agree. But what else? The hand, yeah. Does anyone know the name for this? What is this called? False positive, good. This is called a false positive, right? So this is a false detection. There's not actually a finger here, but our little rule, probably this one, right, thought that the finger should look like this, but it doesn't, right? So it has a false positive. Good, okay. So clearly we're not doing great, right? We need a better approach. Making up rules is not gonna work so well for this computer vision problem. So that's fine. Let's try to find a better way to approach the problem, right? And before we get into finding the better way, there's a couple things we need to do. One thing I really want to emphasize in this module is how we measure the performance of machine learning algorithms and how we measure the performance of any algorithm in computer vision. So as you just saw, right, excuse me, there are different ways that we can be wrong. We can have a false positive, which is where we say that there's a finger, but there actually is no finger. And we can also have what's called a false negative, right? And that's where there is a finger, but we say there's not one, right? And a really common way to represent the performance of a given model is to use what's called a confusion matrix, that's what this is. We're going to be using confusion matrices all the time. They're really, really useful. So we're going to spend a while making sure you guys feel really good about them. And I would say just for now, know that if the actual ground truth label, if it actually is a finger and we say finger, then that's correct. That's called a true positive. If it's not a finger and we say not a finger with our algorithm, then that is called a true negative. And there's two types of false positives, or two types of errors, excuse me. There's a false positive, which is called a type 1 error, and there's a false negative, which is called a type 2 error sometimes. I'll just ask the class for fun. Which one do you think is worse? What is the worst kind of error? Throw it in the chat window. Thomas says false positive. Manashwara says false positive. Okay, false negative. Yeah, so yeah, I kind of tried to trick you a little bit. It really depends on the application, right? Let me ask you this. If this was a test for cancer, right? This was a cancer test instead of a finger test, right? What would be worse? False negative, false positive? Yeah, probably false negative, although both are bad. But false negative for a cancer test means that someone does have cancer and you say they're all good, right? You say they don't have cancer. That's really bad, right? The other one is bad too, but I would say for disease testing, false negative is probably worse. But yeah, it very much depends on the application. There are other applications where false negatives are not really a big deal. So it really depends on what you're doing. But just keep that in mind. The performance of your model depends on your application, or how you evaluate the performance of your model depends on your application. Okay, so the last thing I'll do in this notebook, and then we're going to hop to the next notebook. We're doing pretty well on time, which is great. There's one last thing in machine learning that we need. So we need labels. And we're going to get our labels in this case. We're not going to have to make them ourselves, which is nice. A lot of times you spend a lot of time making your own labels. Here, the camera that we're using, which I showed you back in this notebook, it's called a Leap Motion camera. It includes some hand tracking software, excuse me, which I have hijacked to make this challenge for you guys. Excuse me, I had to clear my throat. Okay, so this allows us to actually identify fingers using the software built into this SDK that comes with this camera. So I have used that and I've packaged it up in a way that actually gives you the labels. So for these images for your data set, for your training data set, you're going to know which pixels correspond to fingers. The labels are not perfect. They're a little bit off here and there, but overall they're pretty good. And we're going to use these labels, hopefully, to train an algorithm that's going to learn what a finger looks like, so we don't have to make up rules. That's the idea here. Excuse me. Okay, the last thing I want to do before we move on to the next section is we will compute the confusion matrix for our rule-based algorithm. Right, yes, cool. That's the last thing we'll do here. So this little block of code is computing the performance for our 30 different decision rules that we made. And I think I might go ahead and hop to the next lecture. We're going to talk about this in more detail in the next lecture. That's what we'll do. We'll start up there right in the next lecture. Cool. Okay. So let me hop over here to our first machine learning lecture. And I think we're going to pick off right where we left off, right? Yes. Yep, cool. Okay, great. All right, so again, just for a little bit of context, we have, and the videos will underline all of this, we've tried to make up some rules. It didn't work so well. So the idea here now is can we write an algorithm that instead of us having to develop our own rules, right, can learn the rules from data, right? That's the whole premise here. Can we do that? How do we do it? How does it work? What's the deal? Okay, so let's get into it here. And just to remind you, we do have these labeled examples that we got from the Leap Motion software. And let's see here, what do I want to show you real quick? Okay. So just to kind of show you some statistics from the data real quick. Okay, yeah, actually, let's get into this now. So I'm using that same method I used in the previous lecture, but I want to go ahead and talk about it a little bit more. So I'm using this method called extract examples from list, which just pulls out the data for you to use basically, but I want to make sure that you know what you're getting. So we have this X thing and this Y thing. And here's the thing I want you to think about now. So if I do np.unique, which remember this is going to return all the unique values, going to return all the unique values in a NumPy array. Go ahead and throw it in the chat window. What is going to be the result of np.unique of y? What is inside of y? Any ideas? What do you think the result will be? So we have a 3, okay. 1, 2, 3. Okay, great guesses. So those are wrong. Good guesses though. No one has gotten it right yet. Remember that the data here is not the overall label. It's not whether or not the image has 1, 2, or 3 fingers. We're going to come back to that. The question is, does a given pixel, does a given little 9x9 grid, does that correspond to a finger? So Manessa, you got it right. Sai, you got it right. Good job. Yeah, so it's just true and false. So what we're going to see here is just 0 and 1, because all this label contains, it just tells us, hey, does this 9x9 grid correspond to a finger or not? Let me show you just a little more detail. So let's pick a random index. Let's look at the 1000th example, for example. And I'm going to reshape it, be 9x9, so we can see it. And I think it's going to be upside down. I think it's not a huge deal, but let me just IM show it real quick. So here's the 1000th example, right? I know it's totally empty. That's pretty cool. Okay. And I have a better way of showing these. Do I want to use the fancier method? Yeah, there's this method called pcolor, which is a little bit nicer, but we'll get into that in a second. But the thing to know is this is totally empty. Let me try to find one that's not empty. Let's see. Yeah, there's like part of a hand maybe or something. Hard to tell. But what I want to get at is we can pull in our label. So if I do y, remember the number I chose the 1100th example. If I do y of 1100, I can see that, okay, this is 0, so the label for this is 0, so this is not a finger. I'll do one more little thing just to kind of show you what we're dealing with here. So if I do np.where of y equals 1, this will show us these are all the indices that should contain fingers. And let me do one more little thing. I'm just going to take the first 10 of those. I guess I'm not going to take the first 10. Oh, I know what's happening. This turns a tuple. Yeah, there we go. So these are the first 10 indices that should contain fingers. And if I do the same thing, and I show this image for, let's take the 422nd one, this should look like a finger. Yeah, there's a finger, right? Cool. So hopefully that gives you a little bit more of a sense for the data. So again, X contains the little patch data. It's kind of our images. They're just all like 9x9 images. And then the the Y vector contains the labels. It contains a 0 or a 1. 1 if that row corresponds to an image, and 0 if it does not. Oh, sorry, corresponds to a finger. Excuse me. It contains a 1 if that row corresponds to a finger. Okay. Okay, so let's get into it in more detail here. And just to show you a couple other things. So here I took the sum of y equals 1. Why did I do that? Let me kind of scroll up from my description. What does this tell me? Throw it in the chat window if you know. What am I trying to figure out here? What does that 495 represent? Kind of, yeah. So it's the number of pixels, yeah, number of ones, how many trues, sure. But what does it mean about the problem though? It's how many of what we have? How many? You're kind of getting there. Where are finger pixels on? Yeah, it's how many of those 9x9 grids we have that correspond to fingers. Yeah, it's how many actual finger pixels we have. Not the total number of fingers completely, but it's how many of all the little 9x9 windows, it's how many of those correspond to fingers. And it turns out 495 of those little 9x9 patches correspond to fingers. And there's 7,867 examples in general. And if I do the difference, this is the number of non-finger examples. Okay, so that's just a little bit about our data. And now I want to have a closer look at our example. So I've added just a couple other support functions here. This finds the unique rows, for example. What I want to start looking is the distribution of our data. So what I've done here is I've said, okay, of those 7,000 or 8,000 examples of 9x9 grids, what's the most common pattern, right? What's the most common repeated pattern? And the answer is, and remember, this is all derived from those original images, right? So everything comes from these images, and I'm just taking them and I'm breaking them apart into 9x9 grids. And for each grid, I'm also doing a binary operation to make them ones and zeros. That's all the pre-processing I'm doing. Now, what I want to get into, just a quick question for you. Why is this the most common pattern? Any ideas? Why are we seeing this empty grid as the most common pattern that shows up in our data set? Yeah, so Austin, good. It's the background. Perfect. Pujab background, perfect. Yep, so this is the background. So all that background space is just white. It's just empty. I know it looks black here, but after we do the binary operation, let me show you this real quick. And this will be shown in the video as well. But we're doing this binary operation, so the background is just white and the foreground is black. So cool. So the reason that's the most common pattern is because this is just the background. There's a bunch of examples of background, and none of those contain fingers. The finger should not look like this. Okay, so let's expand this and let's look at the 40 most common patterns. This is what we're going to do now. So as we discussed, this is the most common pattern, this 3270, right? This is the second most common pattern, just this solid block of color, right? This solid filled grid. Does anyone know what I'm doing with color here? What does red represent? What does blue represent? Any ideas? Why have I colored the examples this way? Yeah, finger, not finger, right? So the blue examples are fingers, because remember we have labels, right? And the red are not fingers. Cool. And you can see if you look at the blue examples, like they kind of look like our rules, right? They don't look too crazy. So maybe we're kind of on the right track. So everything blue is a finger example and everything red is a not finger example. And remember that the overall idea here is that we've been given a labeled data set. We have a data set that tells you which pixels correspond to fingers. And we're going to try to use that to learn a rule to find fingers in general. And we hope that that rule extends to data that's not labeled. So in the future, on your programming challenge, I'm going to give you a training set, and then you're going to be evaluated on a test set. And the test set you will not have labels for. And that's generally how we set up machine learning problems. Okay, so that's cool. The next thing I kind of walk through is I want to figure out how many unique examples I have. It turns out I have 3,090 unique examples. But what I really want to get at is here are all the unique finger examples. So I don't think they're going to quite fit on a page, but here they are. So there are 413, I believe. Yep. There are 413 examples of fingers in our data set. Here they all are. And here they are in front of us, right? So there's 413 examples, and these all represent fingers. These all correspond to fingers in a real data set. So it seems like, hopefully, this could be pretty useful to us, right? This could help us maybe learn a rule, right? Okay. So that's just a little bit of analysis of our data. And we're about to try our first machine learning algorithm. So we're going to do a little bit of more analysis and discussion of results first. But before we do that, I just want to kind of set up what we're going to do for the rest of this lecture. We've got about 20 minutes left. So right, we are going to try our first machine learning algorithm. And it's a real machine learning algorithm. It's very, very simple. All we're going to do is this. So we're going to say, okay, here are 413 examples from a real data set, and we know that all of these examples contain fingers, right? These are all examples of fingers. Look at them all, right? They've got different angles to them. It's really nice, right? What if our machine learning algorithm just says, okay, if I see a pattern in the future that looks like this pattern, any of these 413 patterns really, if I see a match for any of these, I'm going to call it a finger. So basically we're just saying, okay, for our first attempt at machine learning, let's let our data, let's let these patterns, let's let them be rules. Does that make sense? So we're saying, okay, here's a bunch of examples. Let's just use these as rules, right? That's the idea. And this is a machine learning approach because we are using data to learn rules. It's just very simple because the rules really are like, here's the code, right? So rules equals finger examples dot copy. So that's our first machine learning algorithm. So we're about to discuss how we're going to measure its performance, and then I'll show you how it does in a minute. Probably 10 minutes we'll get to its performance. But while I'm talking, think to yourself a little bit. How do you think this will do, right? What is your expectation? So don't put it in the chat window or anything yet. Just think, start mulling over it. Hopefully the idea makes sense, right? We've got this data. We are going to, and no need to answer yet. Just think about it. Just think about it. we're going to use these images as rules, right? So we're going to say each one of these, because it's from real data, must be what fingers look like. And if I see any matches to this in future data, I'm going to call it a finger. That seems pretty reasonable, right? Seems reasonable to me. Okay. So that's our first machine learning algorithm. Now, before we analyze its performance, I want to go a little bit further. So last time we discussed and we introduced the idea of a confusion matrix, and we've almost made it to our first poll of the day, so get excited. So we discussed this idea of a confusion matrix, and just to review it with you really quickly, on a confusion matrix, we're going to show the actual labels versus the predictions from our rule or from our model. And remember these 48 here, these are called true positives. And this is where our algorithm is correct. There's a finger there, and we called it a finger. These are called true negatives. There's no finger, and we say no finger with our rule. And there's two kinds of errors we can make. What is this kind of error called again? What is the 447? What is the name of that kind of error? Just throw it in the chat window. Yeah, FN, false negative. Good. So this is called a false negative. And these are called false positives. Perfect. So for the first poll of the day, I'll give you 30 seconds. I haven't told you how to do this, but I think that a lot of you can figure this out. I think you guys are pretty smart. What is the accuracy? So we haven't defined accuracy yet, but that's okay. I think you may have an intuitive sense for what accuracy is. And remember, this is the rules-based classifier we used that we made in the first lecture. So it's those 30 rules basically. So it's not our new machine learning approach yet. This is our approach from last time. It's our 30 rules that we made manually. This was their performance. This is their confusion matrix. And before we evaluate our new machine learning approach, I want to get a baseline. I want to understand, hey, what is the accuracy of our current rules-based approach where we just have those 30 rules? Okay, Arvind and Rohan, are you guys ready with that poll?
Yes, Professor.
Perfect, thank you. Let's go ahead and launch it. Let's do 45. Actually, let's do 45 seconds. So take 45 seconds. See what you think. A, B, C, or D. What is the accuracy of our algorithm? Okay, great. Good deal. So we've got some A's, B's, C's, and D's. D is the most popular answer. Great. All right, let's get into it. All right, so I think I'm actually going to answer this question in Jupyter. So instead of drawing, I'm just going to do a little math here in the notebook. Let me see if I can get a cell. Yep, cool. Got a cell right here. Great. Okay. So accuracy, I haven't given you a definition, but I just wanted to have you take a shot at it first. So the definition of accuracy, it's the total number correct, it's the number of correct identifications divided by the total number of examples. So to compute accuracy, what we'll do is we'll do 48, so that's the number of correct finger predictions, plus remember that these are correct as well. So these are 7,365 examples that we also got correct. And so that's the number correct. And in the denominator, we'll divide by the total number of examples. So we'll do 48 plus 7,365. Yeah, so that formula in the chat window from Sai, that's great. Yep, absolutely. So here I'm going to add plus 7 plus 447. Cool. That's going to give me this number. And now I would like it to be a percentage, so I'm just going to multiply. So yeah, so we get 94%. So the answer is D. So hopefully that makes sense. So to do accuracy, all you have to do is you have to add together the number of correct examples and divide by the total number of examples. Make sure you feel good about this. This is definitely a kind of question I'd ask you on a quiz. Now, here's the thing that I really want to talk about, and we'll get into it in more detail in a second, but just to get you thinking. What we're claiming here is that this rules-based approach from last time, I asked you guys, I said, hey, you know, how do you think this did? And most of you said crappy. You said it did not do well, right? And look at it, right? So this is the correct answer, right? And it's only getting those, right? It only got like a little portion of the right answer. Does this feel like it's performing at 94%? You know, if someone said, if you're a boss or you're working on a project and you said, hey, we developed an algorithm that is 94% accurate at classifying fingers, do you want to see it? And then you showed it to someone and you showed them this kind of image, right? Do you think they'd be impressed, right? And does this really feel like a 94% accurate classifier? And I think the answer is no. Definitely to me it doesn't, right? So that begs the question, what's wrong, right? Why is accuracy not capturing our performance really well, right? So I have one more question for you to think about to kind of close this up. So let's consider a challenge. So I have a challenge for you. So here is our data set, just a different way to look at our data set. So here it is. We have 495 examples of fingers. Here they are, all these blue dots are examples of finger pixels, right? There's 495 of them. And there are 7,372 pixels in these images that do not contain fingers, right? Okay. So my challenge to you is think of a classifier that would achieve 94% accuracy that would fit in one line of Python code. So an incredibly simple classifier, right, on this data set. Any ideas? And you don't have to even write the Python code. Just tell me in, tell me in text, right? So Abhijit is saying prediction equals not finger, all 0. Yeah, that's right. So what you guys are saying is you're saying, okay, my algorithm, my world's simplest algorithm, is just assume that everything is not a finger. And just in words, why does such a simple algorithm, why does that achieve such high accuracy? We'll show the math in a second, but I just want to ask the class. So it's true that if you just say everything is not a finger, you will achieve 94% accuracy. And yeah, Abhijit is right. So the answer is imbalance. Sometimes we call this class imbalance. Because we have so many more non-finger examples than fingers, if we just measure accuracy, it's going to be very misleading. Because if you get all the finger pixels wrong, right, you just say everything is not a finger, you miss 495 examples, which sucks, but that's only 6% of the data, basically. So you still do pretty well. So the math is right here. I've got a little code if you want to walk through it, but basically really all the math we need is really right, where do I get to it? Here, right? So if we just say that everything is not a finger, we miss 495 and there's 7,867 examples. So if we divide that, we actually end up with 94% accuracy. So 94 is not good, right? And the thing that I'm really trying to drive home is that when you're measuring the performance of these kinds of algorithms, of machine learning or otherwise, accuracy may not tell the entire story, right? There's other metrics that we want to pay attention to. And the two that we're going to use in this class a lot are called precision and recall. And there are different ways to measure performance. And there's other ones too. There's things like F1 score and sensitivity and specificity. And in medical research, they use a different set of metrics, but they're kind of similar actually. But there's a bunch of different ways we can measure performance. And in this class, we will use accuracy, but we're also going to use, probably more often, we're going to use precision and recall. And let's get into those definitions. So what is precision? What is recall? So here's how I like to visualize it. So you can think about the performance of your algorithm kind of like a Venn diagram. So we have all the actual fingers in the world. We have all the predicted fingers by your model. And the intersection of those two is our true positives. It's where we get it right. It's the true positives. So recall is a metric that we're going to use. And what it does is it describes, it measures of all the actual fingers in the world, all the actual fingers, how many did we capture? What percent, right? So if your recall is 50%, it means that you correctly captured half of the fingers, right? Precision is kind of the flip of that. So precision says, okay, of all the predictions that I made, of all the predicted fingers, what percent of those are correct? So if your precision is 50%, what that means is that half of your predictions were right and half of your predictions were wrong. So you'd have a 50% false positive rate. So really precision is all about false positives and recall is all about false negatives. So I would encourage you to get really comfortable with these definitions. I would recommend memorizing the formulas. It's really not bad, I promise. And it will really help having these formulas memorized. I don't recommend memorization in general, and we're going to get into that in a big way. But just for a few things like this, I do recommend having a formula memorized, just because it's so helpful and it comes up so often. The other thing that I encourage you to do, and this is just generally true in your education, is I encourage you to spend time working on explaining these concepts in really simple words, right? Kind of my test is if you can explain something to your mom or to your grandmother and they understand it, if you can explain recall to your grandmother, then you've won. That means that you really understand it. So it's worth spending some time just putting in your own words, what does recall mean? What does precision mean? Okay, so we're about to test. We have 10 minutes left. That's actually perfect because we are going to see how our machine learning approach did. We're almost there to see how it did. And just to remind you, remember our machine learning approach was, okay, let's take our data. Let's find all our unique examples of fingers in our data set. There are 413 of them. Here they all are. And let's just say that each one of these is a rule. And if we find any matches that match this pattern, any of these patterns, then we're going to call it a finger. So that is our machine learning approach. And we're about to see how it does. Okay, so let's see. Here we are. Now, I'm going to keep using a table like this throughout this series, and you'll see it in the videos as well. And this is going to basically compare different strategies. It's going to compare different ways of approaching the problem. So what we have so far is we've actually discussed 3 different ways to solve this problem. And just to give you a summary for each row here, we're talking about a certain strategy. We're going to show the predictions of the model or the approach we use. We'll show the confusion matrix, and we'll show the accuracy, the recall, and the precision. The simplest approach we've considered is actually what we call the baseline. This is just assume that all pixels are not fingers, right? And remember that if you do that, you actually get an accuracy of 94%, which sounds pretty good. However, your recall is actually 0. It's not good, right? And your precision, actually, you can't measure it because you have no prediction. So you end up with does not exist. You divide by 0. So that's our baseline approach. And hopefully machine learning does better, right? Now, we also considered 2 kind of rules-based approaches. First, the very first thing we did at the beginning of lecture is we searched for this very simple pattern. We said, okay, if I find this pattern, I'm going to call it a finger. And we ended up only detecting these little green regions. Hopefully you can see those. There's these little green regions. We got those right, but we missed a bunch of stuff. We still had a very high accuracy, but again, that's because our classes are imbalanced. But we had a very low recall. We only captured 2% of fingers, but we did have a good precision. The next thing we did is we said, okay, let's make up more patterns. Let's make up 30 patterns that could represent fingers, and let's try that. And you can see here that we do get a nice little increase in recall. We're up to 10% recall, which is a little better, right? But our precision goes down. Let me ask you this intuitively. Why did our precision go down for the 30 rules? Throw it in the chat window. Why did this go down? What made our precision go down? What do you think? Why did this precision go down? And you can kind of see it if you look carefully. Hopefully you can see this if you look carefully at these predictions. Yeah, the false positives increased, right? Remember that when we went to 30 rules, we increased, and it's going to be, can I do like this kind of? Oh, yeah. Oh, that's nice. Yes. Good. Thank you, MacBook. Okay, good. Yeah, so see these little red areas, right? These are false positives. So these are areas where our 30 rules, remember some of our rules were like just looking kind of for edges, kind of. So we ended up with these false detections. So these false positives, these false detections, these resulted in a lower precision because we have more false positives. So that's what I was looking for there. Let me zoom back out here to the full screen. Okay. Great, so this is our performance so far, and by the end of this series, we're going to have a very high-performing algorithm, and we'll keep building on this chart as we go. Okay, so let's see here. Oh, and just one last comment. We have different colors, so yellow represents false positives, or sorry, false negatives, excuse me. Red's going to represent false positives, and you'll see it like here, those little red specks. Green represents true positives. You can see this little green region here. Let me zoom in a little more. You can see this green region here. And then finally, if it's not colored, it's going to represent true negative. So all the background, we got those correct, but I haven't colored them, so you can kind of see the original image. So that's how we'll visualize our various algorithms' performance. Okay, great. All right, so now we're finally ready. We have 6 minutes left. We're going to actually try our first machine learning algorithm. Cool. And just as a reminder, this was our original data set that we got. We took 3 images, and we have 413 pixels here that each represent or correspond to fingers. And we just took that data. Here's the binary representation, just to remind you that we are operating on binary images. We found 413 unique patterns. That's 1 for each pixel, basically. We did remove a few that were duplicates, but you ended up with 413 unique patterns. And now we're almost there. So we just took a copy of our finger examples to make our rules, and we're about to pass in our rules. I'll show you right here. We pass in our rules into this method I have called show matches. And that is going to show us and visualize the performance of our first machine learning algorithm. So here we go. Okay. So here is the performance, right? So this is the performance on those 3 images of our first machine learning model. So just throw it in the chat window. How do you feel? Does this look good? How does our performance look on these 3 images? What do you think? Are we happy, not happy? How are we feeling? Good, yeah, so Monica feels good. Yeah, good, better. Yeah, right. We're catching these fingers really, really well. So yeah, you're right, Vanessa. There is some false positives, kind of annoying, right? But I mean, what do you guys think about the accuracy, precision, and recall, right? Do you think those metrics will get better? What do you think? Yeah, I agree, right? So let's check it out. Let's go look and see. Let's see if our accuracy, precision, and recall got better. Okay. So I think we're almost there. And actually what I'm doing in this block is I'm just computing the confusion matrix. So here's the confusion matrix, and I'm actually about to ask you a question. Yep, here we go, cool. So this will be our last poll of the day. We have 4 minutes, this is perfect. This will get you to practice your precision and recall math. So please take 45 seconds, and Arvin and Rohan, as soon as you can get the poll up, just go ahead and please start it. And what I want you to do is, this is the confusion matrix from our new approach that we just computed. And I would like you to tell me what the precision and recall are. So please take 45 seconds and see what you think. Okay, great, thank you. All right, perfect. So the most popular answer is D, and the second most popular answer is C. All right, cool, let's get into it. All right, so again, I'll just do my math here real quick. So remember, the recall is the number of actual fingers that we actually captured, right, or the percentage of actual fingers. So to compute the recall, we're gonna do this. We'll do recall is equal to, it's gonna be 495, that's the number of true positives, the number of correct predictions of fingers, oops, 495. There we go. Divided by, and on the denominator, it's going to be 495 again, and it's going to be plus 0, because we're going to add together all the examples of fingers. How many fingers are there in our data set? There are 495. So kind of our recall, or what I think about this sometimes is our capture rate. What percent of fingers did we correctly capture? We actually captured all of them, right? So our recall is 100%. Which is pretty cool. So we captured, we had a recall where we captured 100% of the actual fingers in our data set. Now our precision is a little bit lower. So our precision is equal to 495, again, the number of correct predictions we made. But this time, precision is the number of correct predictions out of all the predictions we made, all the finger predictions we made, right? So here it's going to be 495 plus 16, because that's the number of of times we predicted that there was a finger or that a patch corresponded to a finger. So here we're going to get a little bit of a lower answer. It's going to be 97, right? So for that reason, and I wanted these to go in order, so recall and precision. So the answer is C. So hopefully that makes sense. That's our recall and precision of that detector. And we only have 1 minute left. It's actually perfect timing. So here is our performance, right? So let me zoom in nice and big on this. So here is our detector. We get 100% accuracy, we get 100% recall, and we get 97% precision. So we have won, right? We have kicked butt. We have great performance. So kind of the point of this lecture, or a big part of it, a big theme that I don't want you to forget ever, is that I've kind of tricked you. And some of you may know this, some of you, if you're new to machine learning, may not know. We really can't trust these numbers. So these numbers are pretty much crap. It's not really true. I basically tricked you. But the reason, understanding why I've tricked you is really, really, really important. So I would like you to go think about this. What have I left out? What am I missing? What is not in my analysis that should be? Watch the videos. That will also give you the answer. But I would really encourage you to just go think about it. You know, even if you know the answer, just spend a little time thinking about this, because this is the biggest misconception. This is what almost everyone gets wrong when they first hop into machine learning. It's really easy to miss. It's not obvious. What are we missing? Why can we not trust these numbers? So don't worry about answering right now. Just take this with you, mull it over, think about it. We're going to discuss it next time. It'll be pre-recorded, I think, on Thursday, but that's okay. We'll still get into the answer, and then we'll discuss more next week. And after you've thought about it, then I'd say go watch the videos. So thank you for attending today, everyone. Hopefully you learned something, and do go reflect on this, right? What have I done wrong? Why can't we trust these numbers? All right, well, thanks, guys. We will talk to you next time.